All right, good afternoon, everyone. Does anyone have any questions before I start with the new material? Okay, so the plan for today is to talk about flame stabilization, flame stretch, edge flames, and things like that. And I'm going to start it out with a little bit of, so this is sort of the outline for what we're going to do today. And I'll start out by just talking about some introductory concepts just about flame stabilization and what happens when you don't have flame stabilization, which is where you get flame blow-off. And in general, flames stabilize in regions of very, very high velocity gradients. Those velocity gradients can be shearing type velocity gradients or tangential straining, or they can be regions of very high flow deceleration. So in either case, that sort of raises the question of if you think about what you've learned in combustion about one-dimensional premixed flames, and you've learned about burning velocities and about the structure of those flames, what happens when you take a flame and you put it in a region where there are significant velocity gradients, or if alternatively the flame is not flat, if the flame is curved? And so that's going to lead us to the whole concept of flame stretch. So we're going to talk a good bit about what flame stretch is and then how that influences flame stabilization. We'll also, time permitting, talk about edge flames. The idea there being is that, particularly for the problem of flame stabilization, is the flame has a point where it begins. So the flame doesn't go on forever. So again, if you think about what we sort of introductory combustion where you learn about premixed or non-premixed flames, we don't really think about what's happening at the edges. We think about the flame kind of going on forever, and we talk about the gradients in properties normal to the flame. But at the edge of the flame, you have gradients in the transverse direction, which are just as strong as gradients in the normal direction. And so you have a completely different animal, so to speak. The flame has a unique structure at the edge, which is also a very important problem toward flame stabilization, because that's the point where the flame stabilizes generally is a point where you have an edge. So if we just go to these slides here, now flame stabilization, what this requires is a point where the flow speed and the flame speed match. All right, and so in other words, what I have here, if you remember sort of the nomenclature that I introduced you yesterday, the D denotes displacement speed. So, how many of you are familiar with the differentiation between the displacement speed and a consumption speed? Okay, all right. So most of you are not. So I'll explain it a little bit later. The main point is that displacement speed is the speed with which a premixed flame propagates with respect to some isosurface. So in other words, if you were to take the 300, if you have a reactance at 300K, if you were to calculate the velocity with respect to, say, the 301K isotherm, that would be a displacement speed. The consumption speed, in contrast, is if you were to integrate the reaction rate through the flame and suitably normalize that to get back a flame speed, that would be the consumption speed. And it turns out that for unstretched flames, the displacement and the consumption speed are identical, which is why a lot of basic combustion texts don't even differentiate between them. But when you start looking at highly stretched flames, the consumption speed and the displacement speed become quite different. But the displacement speed is a useful one for understanding flame stabilization, because what that is telling you is how fast, again, some isotherm or some reference isoscalar surface is propagating with respect to the flow. And so flame stabilization requires that a displacement speed match the flow velocity. And so typically where flames stabilize, you find those in regions of low flow velocity. So for example, in an aerodynamically decelerated region. So if you remember yesterday, I spoke a little bit about high swirl flows, which is what I'm showing you here. Here's a high swirl flow. And this is a plinth image of the flame. And this type of flame I would refer to as being aerodynamically stabilized. In other words, it's stabilized. It's not being stabilized by the presence of a shear layer, but rather it's stabilizing in the interior of the flow. And generally what's happening with aerodynamically stabilized flows is aerodynamically stabilized flames is they're somewhat difficult to create, but what happens is that if you can create a region where the flow decelerates rapidly, but yet has high enough velocity that the flame doesn't flash back. So you're kind of trying to strike a balance between having a flame that doesn't flash back but decelerates rapidly enough that you can find a point where the flame speed and the flow speed match. And you find these types, in order to get that rapid deceleration, oftentimes you invoke swirl on the flow, which is where, in swirling flows you can oftentimes find aerodynamically stabilized flames. The other place where flames will typically stabilize is in regions, the other point where you also get low flow velocity is in regions of high shear, right? So this is what I would refer to as a shear layer stabilized flame. So, a very typical geometry might be, if I just draw a picture here, and I have reactants coming in this direction. Well, I have a boundary layer right here, and I have a boundary layer right here, and that boundary layer separates. And so the velocity goes from the very high core velocity towards near zero, right? And so what you will oftentimes see is that the flame might stabilize like that. And so this would be a shear layer stabilized flame. But because, and again, it's stabilizing there because the flow velocity matches the flame speed. But again, the fact that it's sitting in that region of high shear means it's in a region where there's very strong velocity gradients. And so the problem of flame stabilization and the problem of how flames behave, how thermal diffusive fronts behave in the presence of very, very strong velocity gradients are very coupled. Okay. Let me, one other point that I want to make, just as we're talking about flame stabilization and blow-off, is that in many cases, in realistic type combustor geometries, there are multiple flame stabilization locations. And in fact, what I've shown you here is a series of images. Let me just draw you a picture of what this is an image of. So this is the geometry. So we have flow coming through an annulus, and the flow is swirling. And so because of that flow swirl, we're going to have vortex breakdown. We'll have a stagnation point in the interior of the flow. So what that means is, and also oftentimes in swirl flows, you have a center body in the flow because it's difficult to not. Otherwise, it's very easy for that vortex breakdown bubble to penetrate into the center of the flow. It's hard to not make the flame flash back up the center. So you oftentimes put a center body in swirling flows. So that's what we see here. But what you can see here is if this is imagine this is an axisymmetric geometry, that you have this shear layer here, these go together. The flame could sit there. You have this shear layer here, those go together. The flame could sit there. You also possibly have a rotating pocket of fluid right here if the flow is swirling. So the flame might be able to stabilize out in front of there because the flow velocity would be low, right? So where will it sit? And the answer is it can sit in any one of these spots, and so you could have a whole family of different flame shapes. So for example, you could get a completely aerodynamically stabilized flame. None of the pictures here are aerodynamically stabilized, so I'll just draw one for you. So an aerodynamically stabilized flame might look something like that. All right? Or if the flame could somehow attach itself to this outer shear layer, the flame might bring itself back around. It might look like this. Look something like that. Where the central part is propagating into the reactants because the flow velocity is low enough for the displacement speed to match the flow velocity. And then it's sitting in the shear layer here because the flow velocity is also low. Or, how do I get rid of my red line? You could get flame might sit in the outer shear layer, but it might also sit in the inner shear layer. And it would look like that. So what you would have is a stream of reactants coming in, and then they're being converted. If this is a premixed flame, they're being converted to products. Thank you. As they pass through the flame, right? So you have reactants. Oops, I don't need it to be that thick. So reactants on this side, products on that side. So this is going to be a very typical flame shape as well in this kind of geometry. Or, while we're just laying out possibilities, sometimes what happens is the flame might just sit in the inner shear layer and spread all the way to the wall like that. So I just drew a whole bunch of different flame shapes. And in fact, you can see some of these, and these are different line of sight views. This flame right here is just kind of floating out there in free space. This would be an aerodynamically stabilized flame. Whereas this flame right here is clearly riding in the shear layer. You can see it spreading from the inner shear layer, spreading to the wall. These are line of sight views, so it's a little harder to see. This flame right here is stabilizing in the inner shear layer and the outer shear layer. Oftentimes what we find with these kinds of geometries is that the relative degree to which we get aerodynamically stabilized flames is a strong function of how big this bluff body is. So in fact, this sequence of images was taken in our lab as we're increasing fuel-air ratio. So this would be a very high fuel-air ratio, and the flame can sit in the both shear layers, very, very high shear regions. And as we drop the equivalence ratio, what happens is the flame in these outer shear layer locally blows off. All right? So the flame can't sit here anymore, so it moves to this shape right here. And it's very discontinuous. Right? There's a step jump. There's decreasing equivalence ratio, the flame length is changing a little bit, and then all of a sudden, bang! You completely lose that outer flame, and you end up with a shape that looks like this. Or if you keep decreasing the equivalence ratio, you can all of a sudden the flame can just lift off of the inner shear layer, and you end up with something that's aerodynamically stabilized. And so this is oftentimes what we see in real systems, where you get these discontinuous changes in flame shape, where you essentially have local blow-off. The flame is not globally blowing off. Oh, and by the way, if I go back to this picture, if I were to drop the equivalence ratio still further, and if the flame couldn't stabilize aerodynamically, then it would leave altogether. And then that would be blow-off. The flame is gone. But you can see that there's this problem of local blow-off, and I'll put that in quotes, where the flame can't sit in one region, but if there's other regions that it can sit, it will just change its shape. So these are different topological configurations of the flame position based upon where that flame can stabilize.
Question?
Yes?
Can a flame be simultaneously stabilized?
When you say two mechanisms, you mean in two locations? Oh, absolutely. That was one of the pictures. Let me go back and I'll draw that picture for you here. Oh, I have it right here. This one. So this flame right here is stabilized in the outer shear layer, and the central part is aerodynamically stabilized. Yep.
Previous experiments, so the Reynolds number is kept constant for all the experiments?
For the data I showed you in the previous slide, yeah, fixed velocity, and we drop fuel-air ratio. Yep. Yes?
Without changing any operating conditions, that the flame attached to some region gets attached to some other region without leading to large-scale oscillations.
So you're asking if it can jump between two stabilization positions? Absolutely. It will. We sometimes see, like for example, it'll be bouncing, or what you sometimes see also is the flame starts to come back around, and then it gets kicked back off, and it comes back around, and then it gets kicked back off.
So when that happens, does it leads to large-scale oscillations, or is it without going to instability?
Well, during instabilities, you will oftentimes see that type of behavior. And so
I'm asking you, without going to instability, is it possible to observe this behavior?
it is, yeah. You can see kind of a chaotic, intermittent flipping back and forth. You do see that. Okay, yeah, and so this is what I've done is I've just sketched out some of these different flame shapes that you can get. And so what you can see is just these flames clearly have completely different topological features. So if you were to do an OH, if you were to do plinth imaging or something like that, OH or CH plinth imaging, you would see completely different types of flame shapes. The other thing is that happen is you can imagine as the flame is jumping from configuration D to C, the flame length is basically going to double, right? It's going to take twice as long to consume all that same amount of reactants. And so you're going to see a completely different length of the flame. You'll see, and therefore that would affect, if you had thermocouples along the wall, you would see the temperature distribution be quite different. And these are not smooth continuous changes, they're discontinuous changes. Okay, anyway, that's an overview, just kind of a quick motivation on flame stabilization. Now I want to move into talking about flame stretch specifically. So again, the key motivator is that this flame stabilization problem or lack of flame stabilization, if I talked about local blowoff, for some reason the flame cannot anchor in a given configuration, presumably because it's locally extinguishing or it's locally blowing off. Well, why is that? Well, we believe that in many cases that is related to stretch-induced extinction, or that the local flow velocity is higher than the stretched flame speed. So now what I want to do is move into the second part of this talk, which we'll spend most of the rest of the day on, which is stretched flames. So as we talk about stretched flames, let's just quickly review sort of a flat 1D premixed flame. And so if we have a one-dimensional planar flame that's adiabatic, then the burned gas temperature will equal the adiabatic flame temperature. And we can also calculate a mass burning flux, or a rate that the flame is converting reactants into products per unit area of the flame, and this is all for premixed flames. So the product of the unburned density times the unburned velocity will equal the product of the burned gas density times the burned gas velocity, which we'll call the mass burning flux. And then the burning rate are controlled by things like thermal diffusivities and mass diffusivities, reaction rates, reactant temperatures, pressure, and other kinetic characteristics of your fuel and oxidizer. Yeah?
The consumption speed, right?
Well, if it's a flat flame, consumption and displacement speed are the same. So I'm not going to, we'll for right now, just think it's just the flame speed. We'll talk more precisely when we talk about strongly stretched flames. But really what I want to get into now is what happens if a flame is not flat, or what happens if the flow field isn't one-dimensional. And that's the whole concept of flame stretch. So if we think about this for a minute, what happens if a flame isn't flat? We're going to analyze this or think through this within the concept of one-step chemistry for now. You can analyze these structures with detailed chemistry, and there are some modifications to the picture. But it's very useful to just think fuel plus oxidizer goes to products, and then you end up with this simple two-zone structure where you have this chemically frozen preheat zone, which is where there's a balance between diffusion and convection, and where you have this reaction zone where there's a balance between diffusion and reaction, right? And where the reaction zone is pumping heat back into the preheat zone to bring the temperature up to a point where you can get to sufficient reaction rate, right? So this is a high activation energy picture of a premixed flame with simple one-step irreversible chemistry. Well, so you have this symbiotic relationship between the reaction zone and the preheat zone, where again, the preheat zone is preheating the reactants up to a point where you can get non-negligible reaction rates, and the reaction rate is providing heat back to the preheat zone to bring its temperature up to to the value where you get these reaction rates. Now, and what's happening there is you have this, again, you have this balance between, in the preheat zone specifically, you have this convective diffusive balance. So what I want to do here is I want to just think about energy conservation for a minute, and I want to, here's a stream tube, okay? So a stream tube is a line that is, by definition, parallel to the velocity vectors. And so this is the direction, the stream tube denotes the direction of convective fluxes, right? So by definition, everything that's flowing in, all the convective flux that flows in at the bottom of the stream tube is flowing through the top of the stream tube here. There's no flow through the side of a stream, no convective flow through the side of a stream tube. Now, all right, so we have there's a certain enthalpy flux through the convective enthalpy flux. Yes?
Yesterday, in one of the figures you showed that because of the curvature effect, the stream, the velocity vectors converge.
Yes.
Why don't we see that?
Well, you're absolutely right. So think of this as a I'm not going to add that additional wrinkle. Right, but yeah, so certainly when you curve the flame, it distorts the streamlines. Yes, good point.
That thing happens in the preheat zone or even before the flame actually, the flow actually interacts before the flame.
So in a real exothermic flame, the stream tubes will definitely curve through the preheat zone due to gas expansion.
Not before the preheat.
They will also, you will see even before the preheat zone, you will see them curve. So now what we also have is we have diffusive flux, right? So we have high temperatures here, low temperatures here. We know that diffusive fluxes occur along directions normal to isotherms, right? So if we were to draw lines of constant temperature, you know, like this and like this and like this, that there is conduction of heat, diffusive heat flux normal to those isotherms, right? And so what I'm trying to draw with these this solid black line as shown here is the heat flux vector. And so there is heat flux coming back. But one of the things that's interesting you can see is happening here is that within the control volume itself there's heat flux back, but also because this flame is curved, there's actually heat flux through the side of my stream tube, right? This would not happen if the flame was flat. Right? So you get some non-local effects going on. There's convection, there's this, that if the flame is flat, you would have a balance between the convective enthalpy flux going in this way and the diffusive enthalpy flux going that way. What you have here now is you have convective enthalpy flux, but the energy in this control volume, there's actually an increase in enthalpy in this control volume because of diffusive heat flux through the sidewalls, right? So that's one of the things that curvature does, is it modifies this relationship between the preheat and the reaction zone. Is that the other thing? But there's something else that happens as well. You also have species gradients, right? You have high fuel concentrations in the reactants, and at the exit of the reaction zone, you have low concentrations, and so there is also mass flux, right? Again, there's flux of reactants along lines that are normal to iso species concentrations lines, and so you will also get. So what I've drawn with this dashed line are lines of mass flux of your reactants. And you can see that also because of streamline curvature, because of this curvature, you will actually create the situation where you're losing reactants outside your control volume. Okay? So as we'll talk about later, this is an example of a stretched flame. All right? And the key thing that's happening here is that the reason that this flame is stretched is because convective fluxes and diffusive fluxes are not aligned. All right? Yeah, excuse me. Did I say mass flux? I meant convective fluxes and diffusive fluxes are not aligned. And so that modifies that relationship between the reaction zone and the preheat zone. So I hope that gives you some, we're going to dig into this in more detail, but that gives you some foresight into that something's going to be different when you have a curved flame like this, or more fundamentally, as we'll talk about in the next slide, when convective fluxes and diffusive fluxes are not aligned. All right, yes?
The curved flame, the flame speed doesn't change, but it tends to propagate.
Hold on. When you curve a flame, if the flame is stretch sensitive, the flame speed will absolutely change.
But if you have a additional heat flux on the sides, it will try to increase the temperature of the reactor.
It will.
Flame speed is direct relation to that.
That's right.
So shouldn't the flame speed also increase?
It will. The heat flux effect is going to try to drive up the flame speed, but you're going to be losing chemical. So you're basically gaining thermal energy. You're losing chemical energy. And as we'll talk about later, if the Lewis number is exactly equal to 1, those two effects balance each other out, and there's no net change. But if the Lewis number is not equal to 1, depending upon whether it's greater than 1 or less than 1, you could either, if you add up the chemical energy loss and the thermal energy gain, that number could be greater than 0 or less than 0, and therefore the flame temperature could be higher than the adiabatic flame temperature or lower than the adiabatic flame temperature, and therefore the flame speed could be higher than the unstretched flame speed or lower than the stretched flame speed. Well, this is one example. Here's another example. What happens if your flow field isn't one-dimensional? So a good example of how to do that is in a stagnation flame. And so Professor Seshadri showed a configuration that he has in his university yesterday of a stagnate, where you stagnate two jets into each other. Another way to do that is to take a jet and stagnate it into a wall. So what I've drawn here is a wall. Imagine you have a jet of fluid, and it's going like that. All right, and so if I draw a stream tube, again, I'm going to draw my stream tubes as looking like this. So now, again, what I've drawn here is my reaction zone. Here, this line is my preheat zone, and just to keep life simple, I've assumed that the flame is totally flat. And you can see that you're going to have convective enthalpy flux coming in here, through here, and going into the reaction zone there. And if I do an energy balance on my preheat zone, you can see that in this configuration, I'll actually be losing thermal energy out of this control volume, but I will be potentially gaining chemical energy through species diffusion. Okay, and as I mentioned previously, so the common theme to both of these problems is that you have a misaligned convective and diffusive fluxes. Now, it might be hard for you to see the connection right away of this to for example, flames sitting in shear, in regions of shear, but I'll show you later on how you can actually how you can understand when you have velocity gradients along the flame, how those cause convective and diffusive fluxes to misalign. Okay, so this is our intro to flame stretch. So I've just reproduced those two pictures, and I want to emphasize that right now I'm focusing on stationary flames. There's an additional mechanism for flame stretch if your flame is moving, and that also changes the balance between the reaction zone and the preheat zone. But as I was, and this just shows in math that the arguments I was making is that your steady state energy equation has this form in the preheat zone. So there's no if we assume that there's no reactions because I'm in the preheat zone, I have a convective enthalpy flux term, and I have an enthalpy diffusion term. Here's my heat flux vector that's given, my enthalpy diffusion term here. I have a heat flux term, which is, I'm just to assume is Fourier conduction, and then you have this mass diffusion term. And so as we talked about, that there's this balance between convective enthalpy flux coming into my control volume and also this diffusive energy flux, and that there are two ways in which we can have diffusive enthalpy flux. One is through heat flux through temperature gradients. The other is through chemical energy flux associated with species mass fraction gradients. And so really the major question here is that the mechanism through which curvature or flow inhomogeneities can impact burning velocities and flame temperatures is if there is a net enthalpy loss or gain inside your control volume, or if there's a change in composition inside of the control volume because of diffusive fluxes through those lateral surfaces. All right? So in other words, if I'm losing more energy through the side walls of my stream tube than I'm gaining, then I'm going to be losing enthalpy flux. And just from a global energy balance, the flame temperature is going to have to be lower than the adiabatic flame temperature. Whereas if I'm gaining more energy through those sidewalls, then again, from a global energy balance, then the flame temperature, you can actually have a super adiabatic temperature where the flame temperature is higher than the adiabatic flame temperature. The other mechanism is if there's a change in composition inside of the control volume. I haven't talked about that yet, so let me just say a few things about that. Suppose I have a lean hydrogen air flame. All right, so we know, and it's very lean. All right, so we know that hydrogen, much lower molecular weight than oxygen and nitrogen, and it's going to be much, much more diffusive. And so in the same way as there would be, and so if you have, you're going to have more hydrogen, more oxygen here than you'll have here, right? So both of them will be diffusing in this direction. But then the next question is, well, will they diffuse at the same rate? And the answer is no, right? Because hydrogen is so much more diffusive. You, in fact, will be losing more hydrogen through these sidewalls than you will be losing oxygen and nitrogen. And so that means that you'll actually have a change in composition inside the control volume. If you started out, if your global fuel-air ratio is lean, locally the fuel-air ratio inside that control volume could be even leaner, right? And so you have a mechanism for a change in composition. So there's really, so this question here, is there a net enthalpy gain or loss or a change in composition inside the control volume? These are influenced through two mechanisms. One is a Lewis number effect and the other is a differential diffusion effect. All right? And I want to emphasize they're oftentimes for a given fuel, they are related to each other, but they're completely distinct mechanisms. The Lewis number effect is really looking at the difference between mass and heat diffusion, right? And so, for example, for this flame right here, we said the control volume, this preheat zone control volume, it's gaining, there's a net enthalpy diffusive flux through heat conduction, but it's losing enthalpy through, it's losing enthalpy because there's a chemical energy leaving because of mass flux. And so the balance of which effect is more important is controlled by the Lewis number, right? So for this example, if the heat flux, if alpha is greater than D, than the diffusivity, then you will be gaining more thermal energy than you're losing chemical energy. The flame temperature will be higher than the adiabatic flame temperature, and the flame speed will be higher than the unstretched flame speed. Yes?
But sir, you told the streamlines will be converging there.
Yeah. So again, when you throw all the effects in, these streamlines will be curving as well, and that also changes the picture. But the same basic idea still holds. When you have these negatively stretched flames, you're going to have lateral diffusion through the sidewalls. Yeah, and I'm not trying to shove that under the rug. I'm just trying to not introduce too many things at the same time. I just want to show how the fact that once you have curvature, it creates this. Curvature creates a mechanism for convective fluxes and diffusive fluxes to not be aligned. Is the main point that I want to make, without trying to draw too many lines with curvature on them. Yes. Well, so it depends on the definition, the direction of the stretch. We're going to get into this a little bit, so just give me a couple minutes. For this example I gave you, right here, if alpha is greater than D, flame speed is going to go up. It's going to be higher than the unstretched flame speed. Flame temperature will be higher than the unstretched flame. The temperature will be higher than the adiabatic flame temperature. So that's one mechanism, is the Lewis number effect. The other is the differential diffusion effect, is that if the diffusivity of your species are different than each other, they're going to be diffusing at different rates, right? So the example I just gave you of hydrogen and oxygen, that since the hydrogen is much more diffusive than oxygen, that in this configuration right here, since the fuel is going to be diffusing in that direction, you're going to be losing hydrogen at a faster rate than you're going to be losing oxygen. The local stoichiometry is going to be lower in this control volume than the global approach flow value is, right? Whereas if this mixture started out rich, if the fuel-air ratio was less than 1, it would be, the stoichiometry would be getting driven towards 1. Okay. All right. So the next two slides will unpack these in a little bit more detail. So let's start by talking about Lewis number effect. So if the Lewis number is 1, so the thermal diffusivity and the mass diffusivity is the same, you will have no net enthalpy loss through the lateral surfaces. And to first order, at least, for what are called weakly stretched flames, the effect of flow inhomogeneities or flame curvature does not impact the flame speed. However, if the Lewis number is greater than 1, so in other words, if alpha is greater than D, the heat flux term is going to be greater than the mass flux term. And so for this example here, and I'll explain why this is negatively stretched and this one's positively stretched later. But for this example here, the negatively stretched flame, there's a net enthalpy flux into the control volume for this picture here, right? Whereas this picture here, since you're losing thermal energy, for this positively stretched flame, there's a net enthalpy flux out of the control volume. Okay? Now, if the Lewis number is less than 1, everything flips, right? So going back to this picture, since I'm losing chemical energy through the sidewalls, and because the mass diffusivity is higher than the thermal diffusivity, I will actually have a net enthalpy flux out of the control volume. Whereas for positively stretched, I'll have a net enthalpy flux into the control volume. And so the key point I want you to see here is life's really interesting, right? That the effect of, that you get, depending upon whether the flame is positively or negatively stretched, you get a sensitivity that goes one direction or the other. And depending if the Lewis number is greater than 1 or less than 1, the sensitivity goes one way or the other. Same way, now if we think about differential diffusion, and I already said a lot of this. Let me just... If we think about differential diffusion, the example I gave before was hydrogen air, but here I have it for methane air. But that if we think about this negatively stretched flame, which could, for example, be an approximation for the tip of a Bunsen flame. In that case, methane is lighter than oxygen, so it's going to diffuse faster. And as I talked about, the concentration inside of methane inside this control volume, or of hydrogen, or of any fuel that's less diffusive than oxygen, it will decrease. So, if your overall equivalence ratio is lean, then locally inside the control volume, phi is going to be made even leaner. And what that means is the temperature is going to be lower than T adiabatic, right? In contrast, if your overall equivalence ratio is very rich, then locally in the equivalence ratio, phi is going to be made leaner. It's going to get pulled towards stoichiometric, and the temperature will be higher than a T adiabatic, which will be calculated at your global phi. Right? So what this shows you is that the local fuel-air ratio, differential diffusion can change your local fuel-air ratio from your global value of the reactants. Right? So if you have perfectly premixed reactants with some fixed value of phi, some fixed value of fuel-air ratio, the local fuel-air ratio at which the reactions are happening can be quite different due to differential diffusion effects. And in fact, there's some direct numerical simulations that, for example, Jackie Chen has done, and you can see these very, very strong differential diffusion effects, particularly with hydrogen. Hydrogen flames, the differential diffusion effects are very, very, very strong. Now, if we take, so this would be a fuel that's lighter than air, and you can see that depending upon whether the equivalence ratio is greater than 1 or less than 1, for a negatively stretched flame, you can get two different trends. Now, everything will flip if this flame was positively stretched, right, from what I just said here. Now let's think about a fuel that's heavier than air, like propane. So propane's heavier than oxygen, so going back to this example, it's going to diffuse more slowly, right? And so if you start out lean, the equivalence ratio is actually going to go up. It's going to go in the control volume. It's going to get pulled towards phi equals 1. And in fact, what that would mean would be that the local flame temperature would be higher than the adiabatic flame temperature calculated from your approach flow stoichiometry. Right? So all the trends that I just said here flip for a fuel that's lighter than air. They flip for a fuel that's heavier than air.
Compare the diffusive flux with respect to the convective flux, convective flow flux. I'm talking about the flow velocity compared to the diffusion.
Mm-hmm.
In any case, they might be smaller. The diffusion flux might be.
No, because remember what controls the thickness of a premixed flame. What's going to drive that thickness is going to be, the flame is going to set itself to a thickness where convective and diffusive flux is balanced. You can, in fact, that's a quick and easy way if you forget how to scale a formula for flame thickness, premixed flame thickness. Just balance a convective time with the diffusive time, and that's how you get flame thickness. Yes?
Stabilized wherever the flame velocity matches the flow velocity.
I'm sorry, one more time?
The flame is stabilized wherever the flow velocity matches the flame velocity. And going like that, the center around the axis should have the maximum flow velocity. So which means at the tip, I would expect the velocity to be peaking. And there we have the flame also to be almost normal to the flow velocity. So shouldn't we expect a higher flame speed there? And if you look at Ethernet flames, you would say that the adiabatic.
Yeah, okay, great question. So there's a couple things that are happening. So there is, so the question is that if the flow is normal to the flame right here, by definition, the flame speed's got to be really high, right? So first of all, you can lose your flame tip. What can happen is that you will, the flame will actually open right here. But certainly you're correct that in a configuration like this, the flame speed has to match the flow velocity. Recognize that there's a lot of things going on in I'm trying to make just kind of a very notional picture to try to simplify things. But in a configuration like this, the flow velocity can be changing laterally due to the effect of the flame. You have the refraction of the streamlines, which a few people have pointed out. The last thing I'll point out is that there's an additional effect, which I'm not going to have time to get into. Professor Law's combustion book gets into it. A pure flame curvature effect, which also increases flame speed, but absolutely everything you're saying is right on. So, just want to show you some Bunsen tip flame temperature data. This is actually straight out of Professor Law's combustion physics book. And it just shows the points that we're making. And let's just remind ourselves what we just said here. We said that if your overall equivalence ratio is lean, then for a configuration like this, we would expect that due to this differential diffusion effect, that your local flame temperature is going to be lower than the adiabatic flame temperature. And if your overall equivalence ratio is rich, your flame temperature would be higher than the adiabatic flame temperature. Okay, now here's some data that he has published. This is phi. They measured the flame temperature. The solid line is the dependence of the adiabatic flame temperature upon phi. these symbols are the data. Now, it's very clear, first of all, that the temperature, the whole curve is a little bit shifted down from the adiabatic flame temperature, and this is probably due to radiative losses and things like that. But it's also pretty clear that the data is shifted to the right? So you can see that if you can imagine that this, if I took this curve and I shifted it to the right, you can see how it gets pushed underneath. The measured temperature is less than the flame temperature when we're fuel lean, and once we go fuel rich, the measured flame temperature is higher than the adiabatic flame temperature. And so this general trend, this shifting of the flame temperature with respect to the adiabatic flame temperature, that's exactly consistent with what we were talking about here. All right? So this is direct evidence of the importance of differential diffusion coupled with flame stretch on the burning velocity. Correspondingly, if you measured the local flame speeds, you would see that the flame speed, because of its strong sensitivity to temperature, would also be changing. Now, for propane air, the whole thing flips, right? The tendencies are flipped. That now when you're lean, your flame temperature is going to be higher, and if you're rich, it's going to be lower. And you can see that with the data here. So this data right here is propane air, right? This is methane air. This is propane air. And see how now when we're lean, we're super adiabatic, and when we're rich, it's less than the adiabatic flame temperature. They also did one for ethylene, which is this one, C2H4. Now notice that the molecular weight of C2H4 is 28, right? So it's pretty close to that of air. And here you don't really see that shifting to the left or the right. Really all you see is just the whole curve getting pushed down, which again is probably just a heat loss effect. But the major point here is that these measurements are quite consistent with those ideas that we just talked about on the previous slide. In fact, this goes to what we just mentioned here, is if you look at data, these are propane flames, rich, lean. This is methane, rich, lean. This is from this paper here from Professor Law's group from 1984. And so, again, if we think about propane, that's down here, when we're rich, we expect the flame temperature to be below the adiabatic flame temperature, burning rates to be decreased, here to be inverted. And you can kind of, you got to be a little bit careful because of color scales, but it looks like, in fact, this flame tip is extinguished. Whereas here, it's clearly giving off more luminosity. Presumably chemiluminescence, the rate of heat release is augmented at the tip. Whereas if you look at the methane flame, it's a little bit harder to see, but the rich flame, you can see how it's brighter at the tip than the base of the flame. And here, it looks like it's starting to get diminished intensity there. And so people have spent a lot of time so as you can imagine, for a turbulent flame, well, we talked about flame stabilization, but also turbulent flames. Turbulent flames are by definition highly curved and wrinkled and corrugated. They're also in regions of very significant flow inhomogeneity, so you would expect to see these kinds of effects in turbulent flames. So there's a lot of direct numerical simulations out there. This is from the group at Lawrence Berkeley, John Bell's group. This is a propane flame, a methane flame, and a hydrogen flame, all lean. Excuse me. You guys are boring. Gotta shake things up a little bit and keep your instructor awake. I'm struggling with the 10.5-hour time change. But let's see. But here you can see the propane flame. You can see this, and what they did was they plotted the local curvature of the flame front, right? So you can see that there's points where the flame is curved into the reactants and where it's curved away from the reactants and so forth. And you're looking at mole fraction of OH. And so since this is a let's see here. So remember propane, let's go back to this picture here. Propane likes to be lean when you're curved. The part of the flame that's curved like this, which is negatively curved, the negatively stretched part, it likes to be lean. And so if you can see that would correspond to regions of the flame right here, or right here, or right here. And I don't know if you can see it from back there, but you see how there's enhanced OH, probably due to, you have higher temperatures, so your OH levels are going up. Higher burning rates are going to be happening right here. And you can also see the sense, and so what they did was they measured the local flame speed, and this is you see the SC, that's a consumption speed, and we'll talk about what the definition of that is. And you can see this very clear correlation that the part of the flame that's negatively curved has an augmented flame speed. The part of the flame that's positively curved has a diminished flame speed, right? So the value of 1 being right here. Can you see this, or is it behind the podium? Not really. Okay. All right. So the picture gets a little bit murkier with the other. This is beautiful, right? You can see the very clear correlation. It's a little bit murkier here. There's a lot of scatter, but but let's just look at the hydrogen flame, which is the sort of the extreme other example. Now, what's happening is I can't remember what these lines are. These might be isotherms. But now you can see the part of the flame that's positively curved into the reactants. You see that's where the augmented OH regions are. And then if you look at the trailing part, you see how it's diminished. And you kind of have to squint a little bit, but maybe you could convince yourself that the slope of this line is the opposite of that line, although I'm not sure I would even want to buy that. There's a lot more scatter. And I want to emphasize here that with these flames, in a turbulent flame, there's a couple things going on. First, the flow is unsteady, so there's a time lag between the response of the flame and the turbulent fluctuation. And that would tend to cause some scatter. There's also, there's not only the curvature-induced effect, there's also if we think back to these pictures here, you sort of have both things going on, but we're trying to parameterize everything by just the local curvature. All right. Does anyone have any questions? Yes? Okay, that's a very good question. So what you're saying is, since you're going to have both positive and negative curvature, with the overall effect on the burning rate, the turbulent burning rate, cancel? I think that's the question you're asking. So, I think if I were to recast the question, the basic question here is, what is the effect of differential diffusion on turbulent burning rates? Is there an effect, or does it cancel out? And in fact, the effect of differential diffusion on turbulent burning rates is quite strong. They don't cancel each other out. It's there was some speculation in the literature for a number of years that exactly that effect would happen. In fact, if you just read through the literature, people would say, well, regions of positive curvature, negative curvature, they should cancel. Maybe not quite cancel, but overall the effect should be quite small. But I think, I'll tell you what, I don't want to take us too far afield. Thank you very much. But all I'll say is they don't cancel. There's lots of good reasons that they don't cancel each other out. But if you, for example, take a lean hydrogen flame, which has very, very strong differential diffusion effects, and you compare it to maybe a less lean methane air flame that has less differential diffusion effects, and if you were to compare their turbulent burning velocities, if you were to adjust the stoichiometry so that they had the exact same laminar unstretched flame speed, the turbulent burning velocity of the lean hydrogen flame could be 2 or 3 times higher than that of the methane flame due to differential diffusion. But I can explain to you the reasons afterwards. But it's a great question. Yes?
So the positive and negative stress, periodically, for example, whenever negative stress is there, strain reduces and then slow down. And then it becomes opposite stress next instance when it happens?
Yeah, actually, so this brings me to something I was also supposed to talk about. So I talked about the Darius-Landau instability yesterday, which is an instability of premixed flames due to gas expansion. That gas expansion causes the approach flow streamlines to converge or diverge in a way that causes wrinkles to amplify. You also get something called the thermal diffusive instability. And I think I have a slide on this later, but I can't remember, so I'll just say it now. You get the thermal diffusive instability due, even if gas expansion effects were negligible, if you had an isothermal flame, which would be a boring flame, but just if we forget about the whole Darius-Landau instability for a minute and just neglect gas expansion, but just assume that we have a mixture burning with a burning velocity that's sensitive to the local curvature. Imagine that if you had a mixture where if the burning velocity is higher than the unstretched value here and lower than the unstretched value here, you can imagine the next instant of time, since the burning velocity is low, that this would grow. You know, I'm just kind of making this up, but it would look something like that, right? Because here the flame speed is higher, so it would propagate into the reactants further. Here the flame speed is lower, so it would lag back. And so the wrinkle would grow, all right? In contrast, if the burning velocity was lower than the unstretched flame speed here and higher there, then the next instant of time you would see, you know, the flame would be flattening out. So this is what's called the thermal. So in the first situation, the situation that I drew here, this would be a flame that's thermodiffusively unstable. So stretch effects cause a mechanism for instability of premixed flames. And by instability, I'm not talking about like a thermoacoustic system stability. I'm talking about the flame doesn't want to stay flat. You know, we spend a lot of time, particularly people who do kinetics, trying to make nice, simple, flat flames so they can measure flame speeds or measure species concentrations through them. But it turns out that some flames aren't very accommodating. They want to wrinkle. And one of the reasons that they want to wrinkle is because of thermal diffusive instability. In contrast, some flames are very, very accommodating. They're thermodiffusively stable. They will spontaneously smooth out a wrinkle. So you put a wrinkle on them, and they will smooth it out of their own. And it turns out that, we'll talk about this later, but you can parameterize this depending upon the mixture stretch sensitivity, what's called the Markstein number. Yeah. It happens if the Markstein number is less than, if the Markstein number is positive or negative. Yeah, you know, frankly, there's a couple things going on here. I don't like to parameterize it completely by the Lewis number because you have Lewis number effects and differential diffusion effects. I personally like to think about the Markstein number better because it captures both of them in one sensitivity. But yes, I mean, Lewis number less than 1 would be the thermodiffusively unstable. Nominally, Lewis number greater than 1 would be stable. Yes?
Why do we see this negatively curved cracks in hydrogen air, positively curved regions, and not in propane in this image?
Say it one more time.
In this hydrogen air thing, we see negatively curved cracks in positively curved regions. Whereas we don't see that in methane and propane.
Oh, you mean these things?
Yeah.
Oh, that's a good question. I don't know the answer to that. Very good question. You get some really interesting topological features in these flames. Yeah?
These are the results of experimental study or?
No, this is a direct numerical simulation using detailed hydrogen chemistry. Okay, well I want to shift gears a little bit here now and now talk, I've talked phenomenologically, now I want to dig into the math a little bit more. And I'm going to closely follow actually Foreman Williams, who introduced a lot of this stuff. And so the mathematical definition of flame stretch is given here. It's 1 over A dAdt. So where A would denote a, and so what I had, let's just read this. It says flame stretch rate is defined as the normalized differential change with respect to time of an infinitesimal flame surface area element. Okay, so in other words, if you take a flame surface element and you just watch how that flame surface area is either pulled apart or contracted, the 1 over A dAdt is defined as the flame stretch rate. All right, it has units of 1 on second. It's an inverse time scale. You can see that the units of area cancel, and you end up with 1 over seconds. And I want to unpack this a little bit more on the next couple slides here. So here I have an expression. If you actually do the math and you evaluate this expression, so here I have a differential element of flame surface area. I can define a local coordinate system where n is the normal vector, and then the script t. I don't know if you can read these in the back there, but script t would be t1 and t2 are the unit components that are tangential to the flame sheet. U denotes the velocity, Vf denotes the velocity, excuse me, U denotes the gas velocity, Vf denotes the velocity of the sheet. All right? And I'm going to kind of pull these formulas out of a hat, but I want to spend a lot of time explaining them to you. So you just have to bear with me where these expressions come from. The derivations are in Professor Williams' combustion book or in Ed Law's combustion book. But here's a formula for the flame stretch rate. And I've written it the same way, but basically it's du t1 by dt1 plus du t2 by dt2. So in other words, if you take the velocity vector in the so you take velocity, which is a vector, all right, that's given here. You decompose it into the component normal and tangential to that sheet, right? And there's two components tangential. You have t1 and t2. So ut1 denotes the velocity component along the direction of t1. T2 would denote the velocity component along t2. And what you can see here is that the flame stretch rate is equal to the change of the tangential velocity in the t1 direction along the t1 direction. So in other words, if the velocity in this direction is changing, that's going to lead to a stretched flame, right? Or equivalently in T2, if the velocity in this direction is changing, that will lead to a stretched flame. And I'm going to give this by, and this right here, I'm going to call the tangential divergence vector. So I'm going to call it grad t dot ut, but that just denotes this thing right here. So if you think about the divergence, the overall divergence, but if I think about the divergence just along the tangential directions to an isosurface, that's what this is. And I'm going to call this kappa A. This is the stretch rate associated with the changes in the tangential velocity. And then we have a second component here, Vf dot n of del dot n. You may remember from vector calculus that if you have a surface where n denotes the unit normal, del dot n is 1 over the radius of curvature. All right? So what this is equal to then is it's the velocity of this sheet. Remember, Vf is the velocity of this flame sheet. Vf dot n. So particularly I'm interested in the velocity of the sheet in the direction normal to the sheet. All right? So a real flame, it might be moving around a lot. I'm interested in the component of the velocity of that sheet normal to itself. What it's doing tangential to itself doesn't enter this term. And so, keep jumping ahead just to make sure I'm not repeating myself in a minute here. But what you see is this is equal to Vf dot n divided by r. So if you have a curved flame that's moving normal to itself, that will also cause flame curvature. So and I'm calling that kappa B. Okay? So what we have here then is kappa A, kappa B. One denotes if you have gradients in tangential velocity in the tangential direction, or if you have motion of the flame sheet, of a curved flame sheet in the directions normal to itself. So let's talk about both of those. I'm going to call kappa A, I'm going to call that hydrodynamic stretch, kappa A. And it's the variation of tangential flow velocity in the tangential direction. Or equivalently, by continuity, it's the variation of the normal flow velocity in the direction normal to the flame. If you assume that the flow just upstream of the flame is incompressible, if del dot U is 0, then dun by dn will equal negative grad T dot ut. And so this would be an example of a hydrodynamically stretched flame. So we have here, imagine I can decompose the velocity vector here. So here I'm just going to collapse the flame to a sheet, not think about its internal structure. But this flame, if I think about the velocity component, I can decompose it into a contribution normal and tangential to the flame. What you can see is that velocity component is changing along this direction. In fact, it changes enough that it flips from being pointed in this direction here to pointing in that direction there. This is a stretched flame. All right? And in fact, it's a positively stretched flame. So this is why, if we think back to these pictures that I drew earlier, I told you this is positively stretched, and this explains why we call it positively stretched, is because you can imagine if this was a membrane or something like that, and I was pulling on it in this direction there and pulling on it in that direction there, the flow velocity is trying to create flame surface area. Yes?
Then what is the fundamental reason behind strain? It's not definitely the curvature, right? So is it the flux?
So, all right. Flame stretch, there's a couple different ways to think about it. This is the definition Foreman-Williams gave. There's two things. This is what flame stretch is. When we talk, the reason flames are sensitive to stretch is because it changes the energy balance between the between the preheat zone and the reaction zone. Right? So this is what the definition of stretch is. Flames where you have differential diffusion or Lewis number are sensitive to kappa non-zero values because it changes the energy balance. Did that answer your question?
More fundamental. The curvature is not the reason, right?
No. Curvature is not the reason. It's actually, I think I'm going to get to this on the next slide, but just in case, let me draw you a picture. If you'll bear with me for not curving my streamlines one more time. Here's a curved flame. Yep. Let me decompose the velocity into a contribution normal, tangential. Normal, tangential. So what's the fundamental reason that curvature gives you stretch? It's because this term is non-zero. It's because there is a gradient in tangential velocity along the flame.
If somehow I can make that streamline perpendicular, I mean like this, so it will not be stretched.
That would be, if the flame is stationary,
Right.
so that this term is 0, this is an unstretched flame. Yep. And if you can think about it either way, that this flame is not stretched because there's no tangential velocity component. Also, this flame, there's no misalignment of convective and diffusive fluxes, right? So if I can draw my control volume, convective fluxes are now in the exact same direction as diffusive fluxes, so unstretched flame. Yep.
What is the effect of differential diffusion in such kind of one-dimensional? You assume that it's the flow fields are aligned with your plate, perpendicular to the plate, but there is a differential diffusion is being there. The Lewis number is not in it. So
Yeah.
what will be the effect on the?
So differential diffusion, by the way, impacts the burning velocity of even flat flames because it gives you a stratification in fuel and oxidizer composition in the direction normal to the flame. But the curvature doesn't introduce something new that's not already present. Okay, so first point, so so whenever you have velocity gradient, so there's two ways that this term can cause flame stretch. One is if the flow is curving, or the flow is bending with respect to the flame. The other is through flame curvature, that even if the flow is completely homogeneous, if the angle of the flame is changing with respect to the flow, which is what curvature does, that is also introducing this effect. The other way you stretch a flame is if you have this unsteady curvature effect. So in other words, if I have a flame that looks like this, and its radius is increasing in time, so VF is non-zero, right? So it's not steady. That's the key part. Everything we talked about when I did that more heuristic analysis, I said steady. But if the flame is unsteady, if the flame is moving with respect to time, you can imagine if I take this flame, it's going to be getting stretched. I mean, just purely, it's like blowing up a balloon. That would be this term right here. So if you have a stationary flame, if VF is 0, was the analysis, which again was these two pictures that I drew here, then the stretch rate is just purely, we can interpret it as a variation of the angle between the flow velocity and the flame normal, or equivalently as a variation in tangential flow magnitude along the flame surface. So that can be due to the flow velocity changing or the flame angle changing with respect to the flow. Yes?
Only at the edge of the flame, if it is microscopic behavior, not inside the flame.
I'm sorry, say it one more time.
If the flame stretch is at the edge of the flame only.
Is the flame...
If the flame stretch is only at the edge of the flame, edges of the flame, not inside the...
when you say the edge, you mean...
At the edge where the combustion product and the diffusion is taking. We are only at the edge of the edge.
Well, all right. When you say the edge, you mean the front end of the flame? The reactant side of the flame? Do you mean in the direction, when you say the edge, you mean in the direction normal to the gradients? I guess I would say anywhere that this term is non-zero, the flame is stretched. And what we'll talk about a little bit later is for strongly stretched flames, we have to sort of generalize our thinking a little bit, because these definitions apply to a surface. Real flames are not a surface, they have thickness. So you could actually evaluate this definition for you could define isotherms, you could define a stretch rate for each isotherm through the flame, or you could define a stretch rate associated with each isoscalar value. And those values for strongly stretched flames can vary substantially, and things start to get a little bit more ambiguous for strongly stretched flames. We have a couple, actually I guess we have 20 more minutes. So just plugging right along, you can actually, if you take this expression, you can manipulate it and you can write it in an alternative form, which I've written here. And this is just a bunch of math, but there's a couple points that I want to make here. And what I've done is I've decomposed it into two parts. This first part I've called kappa S. The second part I've called kappa curvature. This kappa S term you can see is non-zero wherever you have velocity gradients. Right? You got to have a velocity gradient for this kappa S term to be non-zero. This term right here, you can also see it has a curvature term. It has SU is the flame speed. It's SU divided by the radius of curvature. Notice that this term is not the same as what I called kappa B here, because this was VF. This is the velocity of the flame sheet. This is the flame speed. So what we've basically done is the velocity of the flame sheet, the flow velocity, the gas velocity, and the flame speed are all related. So if you just write VF is equal to U minus SL times N, you can basically take one of those terms and dump it over here, and the other term, the SL del dot N term, gets stuck right here. So again, these two expressions are completely different, are completely equivalent. They just show you two different things. And the reason that I like to show them is I think this one is very intuitive in order to understand what stretch is. that there's this hydrodynamic component and there's this unsteady curvature component. This one right here I like to look at because it also shows you there's this curvature component, and then there's this component due to velocity gradients. So in other words, kappa S is the stretch due to flow non-uniformities, kappa curvature. That's the stretch of a curved flame in a uniform approach flow, right? So if there were no velocity gradients, if you could somehow magically create a flow with no velocity gradients, this would be that curvature piece. Now, one of the other things I want to point out here is that you may remember from, if you've taken an advanced shear fluid mechanics class, there's a strain rate tensor, which we sometimes call, which I'm calling S here. And in vector form, in tensor form, you know, Sij is equal to 1/2 dui dxj plus duj dxi. Does that sound familiar? And so what the strain rate tensor is, it tells you something about straining of a fluid mechanic element. And if you remember, there's two key ways in which you can strain an element. If I take a blob of fluid in an inhomogeneous flow, you can have shear strain, right, where it can go like that. And you can get normal strain where it gets pulled in one direction, squeezed in the other, or it can get sheared, right? Depending upon whether you're looking at the symmetric or the asymmetric parts of S. So one of the interesting things that this expression does is it gives you a relationship between fluid mechanics straining of a volumetric fluid element and stretching of a flame surface element. All right? And this is just my private nomenclature, but I think oftentimes in the literature people use the word flame strain, flow strain, and they use them interchangeably. Or I mean, they use the same word strain in one case to describe what I'm calling flame stretch. And just to keep notation clean, I like to reserve the word stretch for flame stretch, because you're really talking about a surface quantity, the stretching of a surface quantity, and using the word strain to denote volumetric deformation of a fluid. It's not the same thing, right? Because one is you're taking a volume and you're squeezing it, you know, you're either pushing it and elongating it or you're shearing it. The other is you're saying, what happens if I take a surface within that fluid volume? What is that fluid deformation doing to that surface? And this expression right here shows you, whoops, here I have it right here. This shows you how flow straining and flame stretching are related. They're not the same thing. And in fact, you can have a flow with zero strain, where S is 0, and when the flame is stretched, right? So this term could be 0, and you still have these terms right here. Like you could have curvature term. You can also have a flow where there is 0 flame stretch, but the flow is very highly strained. And the way you would do that is if you have a surface, if the flame was oriented in the direction along here, then you can see that this shearing action here would not increase the length of that element. So one is more of a surface, whether a surface stretching, the other is deformation of a volume. So that's what I'm just saying here, is that the stretch rate can be non-zero when the well, yeah, that's true, but that's kind of a boring statement. I didn't mean to say that. Kappa can be non-zero when the flow strain. Oh yeah, no, that's right. That's what I wanted to say. Kappa can be non-zero when the flow strain is 0. So you can have an unstrained flow and a stretched flame, and vice versa. And so sometimes people confuse fluid mechanics straining, flame stretching. They're related. This expression relates them, but they're not the same thing. All right, let's, this goes to a question that somebody just asked me. Let's just talk real quickly about that unsteady term, a motion of a curved flame. And specifically, I'm talking about this term right here. So if you have a flame that's moving normal to itself and it's curved, that causes flame stretch. But if you have a stationary spherical flame where the velocity vectors are normal to the flame everywhere, that flame is unstretched. That was the question somebody just asked me. So just because you have curvature does not mean you have stretched flame. You have to have a misalignment between the angle of the flame and the velocity vector. That is fundamentally the reason that the flame is stretched. It's not the curvature that's the fundamental reason for the stretch. It's the misalignment of the velocity vector with respect to the flame. Yeah?
Can we manipulate our flow field so that these two stretches cancel out and my flame is not stretching?
For certain very, very simple canonical geometries you can, but not in general. Okay, well I want to try to merge the two things that I've talked about. We've talked about it kind of phenomenologically. I've just given you some formal equations. Now I want to talk about, I specifically want to talk about weak stretch effects, because I'm not going to go through the math, but people like Foreman Williams and others have worked these things out. And if you do asymptotic analysis, you can show that in the linear limit of weak stretch, so if the flame is very weakly stretched, so if you just slightly perturb it from a flat surface, it turns out that the effect of those various types of stretch, so I've talked about kappa A or kappa B or kappa S or kappa curvature, they're all equivalent. And we can collect, so whether you curve the flame or whether you put it in an inhomogeneous flow field, all that matters at the end of the day is the overall value of the stretch rate, kappa, on the flame characteristics. And in fact, what we can do then, if we want to write something like the flame speed, and if we're going to measure the flame speed in a reference frame attached to the unburned gases, so that's S superscript U, what that means is that the flame speed is only a function of the curve of kappa, right, of the overall value of kappa. So SU is a function of kappa, and if I want to say, well, what is that functional dependence of S upon kappa? Well, I can expand this in a Taylor series. So I can say, okay, well, if the flame is weakly stretched, then I'll say SU for some kappa value, that'll be equal to the flame speed at kappa equals 0 plus ds by d kappa at kappa equals 0 times kappa. So in other words, you can imagine a graph where maybe if this is the functional dependence of the flame speed on kappa, let's just say it looked like that. And if I'm saying, well, what would be the flame speed, you know, at this point right here? Well, I'm saying that that's going to equal to SU at kappa equals 0 plus this derivative, you know, the slope of this line. That's just going to be ds particularly the slope of this line here times kappa, that would give me that value there. So this thing right here is a very, very important quantity, and it is the slope of this line, right? It measures for me the sensitivity of a weakly stretched flame to stretch. If this line is flat, if that slope is flat, I would have a flame that was stretched and sensitive. This slope can be positive, it can be negative. We call this thing the Markstein, and notice it has units of length. This is meters per second, this is 1 over second, it has units of meters, units of length. And it is called the Markstein length, delta, and I'm calling it delta sub m. And just to be clear that it's the Markstein length with respect to the defined with respect to the flame speed of the unburned gases I'm giving in a superscript U. Now, I want to emphasize something, and we'll get into this a little bit more later, that this definition of the Markstein length, there's not one single definition. It depends on the iso surface you use. I could just as well be looking at the flame speed with respect to the products. Then I would have delta M superscript B for burned gases, which is what I have here. And the Markstein length, that sensitivity, as measured with respect to the reactants is different than the sensitivity as measured with respect to the products. But bottom line is, and for historical reasons, George Markstein, he put a negative sign in front of here, which is why there's a negative here. But this is oftentimes non-dimensionalized, and so the way we do that is we'll normalize everything by its unstretched value. And here I just call that SU superscript naught to denote the unstretched flame speed. So if I take this expression, I divide the whole thing by SU naught to make it non-dimensionalized. In fact, just to be consistent with that, let me just do that. Then what we have here is that the flame speed, the stretched flame speed normalized by its unstretched value is going to equal 1 minus. And what I've done is I've multiplied and divided by a reference length scale. And this is the unstretched flame thickness. So delta F is the flame thickness. The naught denotes that it's unstretched. So notice I've just divided, I've multiplied. And then what this does is it gives me, this non-dimensionalizes the Markstein length. So what I'm doing is I'm non-dimensionalizing that slope, that dimensionless sensitivity by the flame thickness. And then this gives me a non-dimensional stretch rate. And so this is oftentimes called, this dimensionless ratio is oftentimes called the Markstein number. I'm calling it MA. And just to be clear that it's defined as the Markstein number as defined with respect to the reactants, I'm giving it a superscript U. So that's the Markstein number. This right here is a dimensionless stretch rate, calling it the Karlovitz number. So when you simplify it, then this just becomes that this ratio of flame speeds becomes 1 minus the Markstein number times the Karlovitz number. So if the flame is insensitive to stretch, that would be a flame where the Markstein number is 0, and that would just say that SU is going to equal SU naught. And depending upon then whether the Markstein number of a given flame is positive or negative, and depending upon whether the sign of the stretch is positive or negative, so this term can be positive or negative, that term can be positive or negative, those control whether the flame speed is higher or lower than its unstretched value. And so the reason I like to use the Markstein number is if you think about all the stuff that we've talked about to this point, we've talked about Lewis numbers, we've talked about diffusivity ratios, we've talked about if phi is less than or greater than 1. All that stuff is built into the Markstein number. It's all all that stuff is in that. And so, for example, if you have a lean mixture of a fuel that's lighter than air, like hydrogen or methane, or if you have a rich mixture of fuels that are heavier than air, that would be a flame where the Markstein number is negative. And conversely, if you had the opposite, those are flames where the Markstein number is positive. And so I want to, just before we break here, let me just show you some data. This is a measurement of flame speed normalized by its unstretched value. Remember, Karlovitz is the dimensionless stretch rate. And this just shows you that, let's see, this is for propane. It's for a positively stretched flame, and it's showing you that these rich propane flames like positive stretch, right? That when it's rich, as you increase the stretch rate, the burning speed goes up. That the lean flames don't like stretch. The burning rate goes down, and you can see that that the neutral value is somewhere around phi of 1.4. Now, for kind of the heuristic analysis that we did before, we talked about how when the propane flame was rich versus when it was lean. And I was kind of implicitly saying that that demarcation occurred, that the sensitivity would flip at phi equals 1. You can see not quite at phi equals 1. In this case, it's phi equals 1.4. Here's another example. So this is, remember the slope of this line is the negative of the Markstein number, right? So now if you actually extract that, I have a plot here. This is for a bunch of normal alkanes. Now I'm plotting the actual Markstein number as a function of phi. And as we showed here, you can see that the Markstein number of propane is positive when you're below about 1.4, and it flips to being negative when you're above 1.4. You can see that the slope of the methane is the opposite with phi, right? That when you are that it's going in the opposite direction. And again, this goes exactly with the discussion that we gave before when I walked you through that differential diffusion argument. That because methane was lighter than the oxidizer, you'd have a totally different sensitivity than propane, which was heavier than oxidizer. Okay, let me go through one more slide, then we'll take our afternoon break here. So this just shows you some examples for different fuels, all right, how these Markstein numbers differ. What I have here is a plot for different pressures. Now, this is the stretch rate. Now, this is dimensional, okay? So this is flame speed. This is kappa. Here is, I've normalized kappa by the flame thickness in the unstretched flame speed. Now, this actually shows, so to this point, I've only talked about weak stretch effects. What happens if you just very weakly stretch a flame where you can sort of linearize its behavior around small kappa? I'm actually showing you what happens for very strong stretch values, but let's just ignore that for a minute. But what you can see here is that what's happening to the dimensional stretch sensitivity as we go up in pressure. And by the way, the details on this is for a syngas flame, 300K reacting temperature, and we've adjusted the fuel-air ratio at each pressure so we've maintained constant unstretched flame speed. Well, what's happening to the Markstein number? Well, you notice how the dimensional sensitivity of the flame to stretch is dropping as you go up in pressure. Why do you think that's happening? Well, what happens to a premixed flame as you go up in pressure? What happens to the structure? Yes? Yeah, it gets thinner. That's probably the main effect, right? It's thinner. So what's happening here is that the same dimensional stretch value, if we think about our non-dimensionalization here, the same dimensional value of kappa, if you're changing the flame thickness, the flame is getting thinner. And remember, what's ultimately, the reason the flame is sensitive to stretch in the first place is because it has finite thickness, right? If you think about, let's just jump to this picture here. For a given value of curvature, as this flame gets thinner, you can see that that the effect of the misalignment of the convective and diffusive fluxes is going to get smaller and smaller. And so the dimensional sensitivity of the flame to stretch is dropping as you're going up in pressure. But what I want to show you over here is, here I'm plotting the same thing, but now it's versus Karlovitz number, and you can see that the curves show pretty similar dimensionless. They're not exactly the same. There are some differences there, which would be kinetic. But this is an interesting one, and this is just showing you the very important effect of pressure on flame thickness. Okay, why don't we, should we take a break? Okay, till what time? Half hour. Okay, so we'll reconvene at 4 o'clock. All right, thank you.